All right, so I believe we left off here when we were talking about the Bohr model. And so students are usually familiar with the Bohr model, and we're going to go past what you would have seen in high school. But I wanted to show you a traditional Bohr model because it's still useful, even though some of the things, for example, the Bohr model is only good for the hydrogen atom. It's some of the things that Bohr had found was actually still important and used today. So here's an example of a Bohr diagram for carbon, and we can see that you have electrons at certain energy levels, and each electron here, for example, the first two electrons that make up the carbon atom are going to be at the first energy level, which is a certain distance away from the nucleus. And and then, so your first two electrons are at the n equal to 1 energy level, okay? And then the next four are at the n equal to 2 energy level. And so we're going to talk a little bit about electrons existing at certain energy levels, and that's you're going to learn tonight that's referred to as quantum numbers. Every electron has a certain quantum number associated with it, and that is just specifying the energy level that it's at. And so the closer the electrons are to the nucleus of the atom, the lower the energy level they have. So we know that electrons that are in the outermost energy level have the highest energy level, and those are referred to as valence electrons. And so we know valence electrons are really important because those are the electrons involved in chemical bonding. So we're going to discuss more about this, but I wanted to bring this back to you because I know we discussed the Bohr model in class, and I wanted you guys to look at that because we're basically tonight we're just going to sort of expand on what we already know about electrons, and we want to know a lot more about where they're located. So that's sort of the basic idea that we're going to discuss in this lecture. Okay, so we're starting here with section 6.2, the Bohr model. So it's the Bohr model describes the hydrogen atom. And so there are different ways you can calculate the amount of energy needed for electrons to move into different energy levels. Okay, so in 1913, the emission spectra for hydrogen was explained by Niels Bohr. Okay, so he basically initiated the development of quantum mechanics, which is something that he had to abandon his idea of classical physics and trying to explain how electrons behaved, and instead had to adopt a new model and new theories associated with electrons and how they behave. So before Bohr, scientists thought atoms consisted of a tiny, dense nucleus surrounded by lighter and tinier electrons continuing to move about the nucleus. So the classical mechanical description of the atom is incomplete since an electron moves in an elliptical orbit, would be accelerating, and the electron should continuously emit radiation according to classical electromagnetism, and we know that's we don't observe that. So the atomic model prior to Bohr, again, is loss in orbital energy should result in the electron's orbit getting continually smaller until it spirals into the nucleus. We know electrons don't run into the nucleus. So Niels Bohr attempted to resolve the atomic paradox by ignoring classical electromagnetism's predictions that the orbiting electron and hydrogen would continuously emit light. So Bohr incorporated the following into the classical mechanics description of the atom: Planck's ideas of quantization, Einstein's finding that light consists of photons whose energy is proportional to their frequency. So Bohr assumed that the electron orbiting the nucleus would not normally emit any radiation. Rather, the electron emits or absorbs a photon if it moved to a different orbit. The energy absorbed or emitted would reflect differences in orbital energies according to this equation. So the change in energy is equal to Planck's constant times the frequency, which is equal to Planck's constant times the speed of light divided by the wavelength. So EI and EF, EI is initial energy, EF is the final energy, and so notice it's an absolute value there. There's a change in energy. There is positive. So Bohr assumed only discrete values for the energy differences were possible. Okay, so Bohr's expression for the quantized energies here is equal to this new constant here, K, is constant comprising fundamental constants such as electron mass and charge and Planck's constant. So the value of K is 2.179 times 10 to the negative 18 joules. Okay, N can be any integer from 1 on. Okay, and N, of course, represents energy levels. And so each energy level was quantized. So when we went back, going back to the Bohr diagram, you know, every electron's at a certain energy level. The electrons don't exist in between the energy levels. Okay, they're assigned a certain value because they have a certain amount of energy associated to where they are relative to the nucleus. So it's, you know, the amount of energy they have depends on how far away they are from the nucleus. If they're very close to the nucleus, their energy is smaller than electrons that are further away. All right, so with the Bohr model here, you have expressions here where we're involving two different energy levels, and that happens whenever you have an electron that absorbs energy and moves to a different energy level, okay, a different orbit, and then when it comes back down, it has a different energy level, and so we can use this to calculate basically the energy it takes for that transition to occur. Okay, so we spoke earlier about the Rydberg equation, which is very similar to the identical to the Rydberg equation. So here we can see an energy level diagram showing energy levels. Here, energy level of 1, n equal to 1, n equal to 2, 3, 4, and 5. And then you see the energy values associated with each of those energy levels for the hydrogen atom. So the more negative the value is, the lower the energy. So we can see here that value of n equal to 1 has a lower energy than a value of n equal to 2 versus n equal to 3, and so on. So we know for the hydrogen atom, it only has one electron. So, you know, the Bohr diagram for it would be pretty simplified. If you erased all of the electrons here except this one here, that would represent a Bohr diagram for hydrogen. But you still have these empty energy levels, okay? So even though you only have one electron existing here at n equal to 1 for hydrogen, you still have a possibility of an electron having a higher energy value. So one of the most fundamental laws of physics is that matter is most stable when it has its lowest possible energy. When the electron is in this lowest energy orbit, n equal to 1, the atom is said to be in its ground state. Okay, so it's in its ground state because it has an n value of 1 because it only has one electron. But for example, if I'm referring to this electron here, its ground state is n equal to 2 because that's where it's naturally found. Okay, so it's also possible, even though we're talking about hydrogen right now and an electron at n equal to 1 going up to a higher energy level, this electron can also go up to a higher energy level if it absorbs the energy. So here for hydrogen, because it only has one electron, its ground state is going to be when it's at n equal to 1. If the atom receives energy from an outside source, it's possible for the electron to move to an orbit with a higher n value, which has a higher energy. And this is referred to as the excited state. When the atom absorbs energy as a photon, the electron moves from an orbit with a lower N to a higher N. Okay, so when an electron falls from an orbit with a higher N to a lower N, the atom emits energy as a photon. So since the change in energy can only be discrete values, a photon absorbed or emitted can only have a wavelength with a discrete value. It's not continuous. So it has a certain value as well. This explains the line spectra for the hydrogen atom. So here we can see sort of a diagram of this. We see in energy values here increasing as you go from the bottom up. And here we see an energy level of 1, and then we have different energy levels that in hydrogen are unoccupied because hydrogen only has 1 electron. So when the electron, it's 1 electron, absorbs energy, it can move to different energy levels. It can move to an energy level of N equal to 2, or another energy level of N equal to 3, or 4, or 5, or so on to infinity. And then if, like, say for example, it's also possible if it gets bumped up to an energy level of 2, you can then again absorb energy to go to 3, 4, or 5. Okay. Eventually, though, of course, the electron is going to lose that energy. Okay, so it's going to go back down and make different transitions are possible. It can go from 5 to 1, 4 to 1, 3 to 1, 2 to 1. All right, or you can see relaxation even within values other than 1, 5 to 2, 4 to 2, 3 to 2. But when the electron basically loses its energy, it is going to, when it does that, it's also going to emit, basically release energy in the form of light. Okay, and this is referred to as light emission. So here we're going to look at calculation where they're asking us to find the energy and the wavelength in meters of the line spectrum of hydrogen that represents the movement of an electron from a Bohr orbit of n equal to 4 to the orbit of n equal to 6. In what part of the electromagnetic spectrum do we find this radiation? So in this case, I would need our formula here. The change in energy is equal to K times 1 over n sub 1 squared minus 1 over n sub 2 squared. So I look here at my given values here. Let's see if I can. Okay. So with my given values, so I'm given n equal to 1 is 4, so that's the initial energy level of the electron, and then it went from 4 to 6. Okay, so they're asking for the energy amount and the wavelength, and then what part of the electromagnetic spectrum is this wavelength associated with. So here's our formula here to find the change in the energy. Okay, our K value, our constants, 2.179 times 10 to the negative 18th joules. Okay, n sub 1 being the initial, basically the ground state energy level, and then n sub 2 being the excited state energy level. So here I'm plugging in my values here, my K value, 1 over n sub 1, which is 4 squared, minus 1 over n sub 2, which is 6 squared. Okay, and so I do my math here. Okay, and I get a value for the energy level of 7.566 times 10 to the negative 20th joules. So the second part of the question asks us to find the wavelength. And so the wavelength is equal to Planck's constant times the speed of light divided by the energy. So I just plugged in Planck's constant, 6.626 times 10 to the negative 34th joules times seconds, times the speed of light, which is 3 times 10 to the 8th meters per second, divided by our energy value that we got. And then we get, for the wavelength, we get 6 or 2.626 times 10 to the negative 6 meters. Okay, so I convert that to nanometers. Okay, the reason I did that is because for me personally, I find nanometers is it's easier for me to realize what that would be in terms of electromagnetic spectrum. I know they said to do it in meters, but I just convert it to nanometers, and it's 2,626 nanometers. So because it's nanometers, I know, like, for example, 400 nanometers to 800 nanometers, that's in the visible region. Okay, and then I know, like, 200 nanometers to 400 nanometers, that's the UV region. So I know something that's greater than that, so 900 nanometers, and this is like 2000. This is going to be in the infrared region. Okay. So, and if you wanted to, you could look back. And I told you guys you need to kind of memorize this graph here, this sheet, and looking at, here are the wavelengths values associated with, and that's in meters now, not nanometers, but wavelength values associated with different regions of the electromagnetic spectrum. So here, you know, just so you get kind of an idea of what these values are in certain portions of the electromagnetic spectrum. That would be something that would be important to try to memorize as best as you can. All right, so let's see. Here we go. All right, so let's talk about limitations in Bohr's model. So he was able to explain the hydrogen atom fairly well, but when he tried to use his theory for helium, which has 2 electrons, he could not fit his data with his model. So, Bohr's model does not really account for an atom that has more than 1 electron. So you can't really use it to explain electron-electron interactions, okay, for atoms that have more than 1 electron. Bohr's model was flawed because it's only still based on mechanics, classical mechanics, and so the notion of he did explain energy values, and that had how electrons have discrete energy values, and how they can go from one energy value to the other. He explained that, but that was good, but it was only for the hydrogen atom. So there are still some important things, though, that we can take from his work. And so the energy of electrons in an atom are quantized. That means they have only specific energy values. And these energy values are described by quantum numbers, and so we refer to them as energy levels. But we're going to learn tonight how you can assign what's referred to as quantum numbers, which are numbers that are assigned, they're unique for each electron in an atom. Okay, so quantum numbers are integer numbers having only specific allowed values and used to characterize the arrangement of electrons in an atom. An atom's energy increases with increasing distance from the nucleus. So like I said before, the further you are away from the nucleus, an electron has greater energy than an electron that's really close to the nucleus. This discrete energy or lines in the spectra of the elements result from quantized electronic energies. So let me go back to that picture for just a second. We talked about atomic emission. Okay, and I explained this 2 Wednesdays ago when we talked about electrons being excited and going to different energy states, and then coming back down and then releasing light. and this is referred to as emission spectra. And so you're going to see that on our next slide. You're going to see certain colors associated with certain elements, sort of like fingerprints, okay, in a way. And it's sort of a blended color of all the light colors that they emit. But there are ways you can, in the lab, you can look at the flame using a spectroscope, and you're able to see actually the different light bands associated with each color. So it's kind of neat to be able to do that. We're not going to be able to do that on Wednesday, but we will see different colors for different elements. It'll be a blending of all the colors that are emitted because the electrons are being excited and moving to higher energy levels, and then they're coming back down. And when they come back down, they're able to emit light. All right. All right, so here we go. So Bohr won the Nobel Prize in Physics for his contributions. It became clear that most physicists at that time that the classical theories worked so well in the macroscopic world were fundamentally flawed and could not be extended down to the microscopic domain of atoms and molecules. So a proper model of quantum mechanics was later developed to supersede classical mechanics. Okay, so that's what we're going to talk about next. So development of quantum theory. So we're going to extend the concept of wave-particle duality that was observed in electromagnetic radiation to matter as well. We're going to learn how to understand the general idea of the quantum mechanical descriptions of electrons in an atom, and that it uses the notion of three-dimensional wave functions or orbitals that define the distribution of probability to find an electron in a particular part of space. We're going to list and describe traits of the four quantum numbers that form the basis for completely specifying the state of an electron in an atom. So in the next couple slides, we're going to be talking about a lot of theory and how everything was sort of put together and what we understand and about the atom. Okay, so it's important for you to understand the history, but in terms of testing, that when we start to do more specific problems, calculations, and that sort of thing, or figuring out quantum numbers, that's something that you're really going to have to be good at, and we're going to have to take a little time to do some examples so that you're familiar with how to determine quantum numbers for different electrons in an atom. All right, so particles and waves are very different phenomena in the macroscopic realm. So we have a concept of what a particle is. All right, like particles of sand, for example. We know what waves are in terms of the shape and how things can move, like water waves, for example, or light waves. But in the 1920s, it became clear that very small pieces of matter follow a different set of rules for those we observe for large objects. So the unquestionable separation of waves and particles was no longer the case for the microscopic world. So here we see an interference pattern on the water surface. It's formed by interacting waves. The waves are caused by reflection of water from the rocks. So Louis de Broglie, we're going to talk about him, and in 1925 he extended the wave-particle duality of light that Einstein used to resolve the photoelectric effect paradox to material particles. So if electromagnetic radiation can have particle-like character, can electrons and other submicroscopic particles exhibit wave-like character? So we know light can act both like particles and waves. So the question is, can electrons do the same thing? So we get to this point of the de Broglie wavelength is a characteristic of particles, not electromagnetic radiation. So we learned how to calculate wavelength for light. So wavelength for light is equal to the speed of light over the frequency. But for de Broglie wavelength, it's a characteristic of particles, not electromagnetic radiation or light. So to determine the de Broglie wavelength, that's equal to Planck's constant divided by the mass times the velocity of the particle. Or, if you remember from physics, momentum is equal to mass times velocity of the object. So the Broglie wavelength is equal to Planck's constant divided by the momentum of the particle. So Bohr had postulated the electron as being a particle orbiting the nucleus in quantized orbits. De Broglie argued that Bohr's assumption of quantization can be explained if the electron is considered a circular standing wave. Only an integer number of wavelengths can fit exactly within the orbit. Here we see a circle here with a certain radius, and it's shown by dashed lines here. If an electron is viewed as a wave circling around a nucleus, an integer number possible of wavelengths must fit into the orbit for this standing wave behavior to be possible. So, for a circular orbit with radius, the circumference of a circle is 2 times pi times r, and so the de Broglie condition is, in order for, if you could try to fit in an electron moving in the pattern of a wave, it would have to have certain values, certain positive integer values, times its wavelength in order to fit within the circle. So the wave nature of electrons here, C.J. Davison and L.H. Germer demonstrated experimentally that electrons can exhibit wave-like behavior. They showed that electrons traveling through a regular atomic pattern in a crystal produced an interference pattern. Let me show you that here. So here we have 2 slits, and we have an electron source, and we see that they were able to detect an interference pattern as if they acted like there were light waves. And we talked about constructive and destructive interference, and so they're able to see that electrons can exhibit a wave-like behavior. So the interference pattern was strikingly similar to the interference pattern for light. And then in another experiment they did, they had another electron source. Electrons were able to go through slits, and it also, their results showed that the electrons in this case acted like they were particles. And so it appears that while electrons are small, localized particles, their motion does not follow the equations of motions implied by classical mechanics. Instead, some type of new wave equation governs the probability distribution for an electron's motion. So thus, the wave-particle duality first observed with photons is actually a fundamental behavior intrinsic to all quantum particles, meaning that electrons, even though they are particles, they can move around in a wave-like pattern. So this brings us to the Heisenberg uncertainty principle. So Werner Heisenberg determined that there is a fundamental limit to how accurately one can measure both a particle's position and its momentum simultaneously. The more accurately we measure the momentum of a particle, the less accurately we can determine its position at that time, and vice versa. This is referred to as the Heisenberg uncertainty principle. It's fundamentally possible to determine simultaneously and exactly both the momentum and the position of a particle. So here we have the change in x, that's the uncertainty of the position of the particle, and we have the change in the momentum, it's the uncertainty of the momentum in the particle in the x direction. And so basically you can't determine, if you determine one, you can't determine the other. Next, we're going to talk about the quantum mechanical model of an atom. Schrödinger extended the de Broglie's work by incorporating the de Broglie relation into a wave equation. Today, this is known as the Schrödinger equation. The Schrödinger equation properly thought of an electron in terms of a three-dimensional stationary wave or wave function represented by the Greek letter psi. A few years later, Max Born, his contributions to this idea, electrons are still particles, and so the waves represented by the wave function psi are not physical waves, but instead are complex probability amplitudes. The square of the magnitude of the wave function describes the probability of a quantum particle being present near a certain location in space. Wave functions can be used to determine the distribution of the electron's density with respect to the nucleus in the atom. So this brings us to the Schrödinger equation. So the most general form of the Schrödinger equation can be written as H, which is the Hamiltonian operator, times psi is equal to E, which is the energy of the quantum particle, times psi. Psi is the wave function of the particle. E is the total energy of the particle. The Schrödinger's work, as well as Heisenberg and many other scientists following in their footsteps, is generally referred to as quantum mechanics. Okay, so if you make it to physical chemistry, most of what you'll talk about is where chemistry and physics really overlaps, and you'll be learning a lot about. And actually, one of the reasons why you have to take a lot of calculus classes for chemistry is to be able to understand the math behind quantum mechanics. Okay, and it has a lot to do with Schrödinger and this theoretical aspect of chemistry. And it's important because they're really trying to figure out where electrons are located so that they can sort of explain why some chemical reactions occur and some of them don't. Or like if you're synthesizing certain chemicals, sometimes you'll have a certain percent, you'll have reactions where a certain percent will give you one product and then a certain percent will give you another product. And so if you understand the chemistry better, it's possible for you to figure out a way to increase your yields of a certain product over the other, or just better understand how the process works, so you can maybe possibly create a catalyst that would improve that process and getting your percent yield higher, for example. But that's very advanced compared to where we are now in general chemistry. But we're going to continue this discussion in the next video.